Hi, my name is Max Ditson, and this is my charge tapes lab for Physics 2212. So today, we're going to be conducting an experiment to determine approximately how much excess charge is on one charged piece of tape. The reason for this is that we can use our knowledge in physics, the different laws and properties we learn, to observe the transfer of charge on normal objects. So we have three main physics principles we're using here today. The first being Newton's second law. This law basically boils down to force equals mass times acceleration. This will be very useful in finding the force the tapes exert on each other, because the floating tape has no acceleration, so all the force on an object must sum to zero. The second law we'll be using today is Newton's third law. Newton's third law states for every action, there's an equal and opposite reaction. This will be very helpful because once we solve for the force tape A exerts on tape B, we know that is of the same magnitude of the force tape B exerts on tape A. The last law we're using today will be Coulomb's law. This law sets up this very nice equation right here before us, where we can go straight from the force to the charges, and we just know the K is a constant, so we already know that, and we know R, which is the distance between the two objects, which is going to be something that we'll measure. For this lab to work, we are going to have to assume some things. First things first, we are going to be ignoring air resistance. Using our second law equation on the floating tape, we are not going to sum in air resistance, as it is a hassle to quantify. We're just going to use the force that tapes exert on each other and the gravitational force. We're also going to treat the long tape as a single point charge. This will be very helpful in our diagrams, but more importantly, it's going to make it a lot easier for calculations. Lastly, we are going to assume each U-tape has approximately the same charge. We made them the same way using the tape method, where we pulled it off another piece of tape, so they should have around the same charge, but we don't know for certain. The Coulomb law equation uses the charge for both tapes, and since that is two unknowns to solve for, we are just going to treat them as one. So in our equation, instead of a Q1 and Q2, we'll just be using Q squared today. After conducting this experiment, here's the data we got. We measured our tape to be about 0.2 meters, and we know the mass of the tape is approximately 1 gram per meter, so that makes the mass 0.2 grams. After charging the tapes and having them near each other like this diagram, we got a distance of 0.45 centimeters between them, which comes around to 4.5 times 10 to the negative third meters. Now, this is all we need to know to find the magnitude of the charge, but the problem is that we don't know the sign. Whether they were both positive or both negatively charged, they would have repelled either way, so we need to do a new experiment to test for the charge. So we rubbed the pin against my hair and to get it negatively charged, and we put the tape near it to see if it would repel or attract. And we noticed there was a very strong attraction between the two, so we know that our tape would be positive. So here are the results for the experiment. By combining the second law equation with Coulomb's law, we were able to derive an equation for the charge, and after plugging in our data and the constants, we got a charge of 2.12 times 10 to the negative 9th coulombs. From the other experiment, we knew this was a positive charge, and luckily for us, this data is well within the range of what we wanted to get. So here are some other numbers we wanted to find. By dividing the charge by the charge of an electron, we were able to see just how many electrons our tape gained, which in this case was 1.325 times 10 to the 10th electrons. We also wanted to find a ratio of how many atoms gave up their electrons for the tape we used to get this charged tape. But first, we needed to find the number of atoms. By finding the surface area of both the tape and the atom, we found that there were 40 quadrillion atoms in our tape. And after solving, we got a significantly low ratio between the two. This is honestly amazing because it looks like tons and tons of electrons left, but in reality it was barely anything at all. So here's my computational model for the experiment. I have Q1 here in the top right. That's going to be representing the charge of the floating tape, while Q2 is representing the charge of the tape that we held up. I also added the forces on there. I have the gravitational force as well as the forces that the tapes exert on each other. In the code here, I have both the constants and the data that we found, and I created some equations there at the bottom, which gives us those numbers right under the diagram. So that is how we found the charge, the number of atoms, number of electrons, and the ratio of the atoms that lost electrons. And I'll have a link to this in the description below. We also had some post-lab questions we wanted to answer. The first is being, what if electrons had a positive charge and protons had a negative charge? What would change about the observation you made with your tapes and other charged objects? And although all of our data would have been flipped between positive and negative, the experiment itself would still run the same, as the tapes would still have a differing charge causing the repel, and we would have found that our tape was negatively charged, as it would be attracted to the now positively charged pin. Our second question was, why is it important to handle charge tapes as little as possible? And what would happen when the charge tape comes in contact with your hands or other objects? So we actually found out the answer to this one for proper mishandling of the tape. When we first pulled the tape off, we accidentally had to touch our hand, and we noticed that it removes all charge from the tape and it becomes neutral again. So it is very important that when we're handling this tape, we can't let it touch anything, because then the tape would transfer electrons again and that charge would cease to exist.